Okay, so welcome to another one of our weather band webinars. We're thrilled to have Professor Victor Gensini here with us today. He's an associate professor in the Department of Geographic and Atmospheric Sciences at Northern Illinois University. His current research is focused on extreme weather prediction and analysis, especially how those places intersect with climate change. So we're really excited to hear about his latest research and all the wonderful things that he has been looking into. Again, if you do have any questions throughout the presentation, please put them into that Q&A box and we will get to those, or Professor will get to those at the end after he's gone through his presentation. So once again, thank you so much for being here. We're thrilled to have you and really excited that you could take this time to share your information with the weather band.
Awesome. Thank you so much. Wow, almost 200 people on a Thursday afternoon. So many of you all either don't have other Zoom meetings or you're a weather geek like I am. So it's great to see so many familiar names on here. The title, right? Extreme weather analysis and prediction. Certainly severe weather events, tornadoes, hail, damaging winds, they all fall into that extreme weather interface. And so a lot of what I'm going to talk about today is focused on severe convective storms, but does have direct applications to other forms of extreme weather. Interestingly enough, possibly a hurricane landfall on the East Coast here incoming. So direct applications to what we see going around us in all types of extreme weather. So thanks to the AMS Weather Band for having me. I'm going to jump right in because I do have a lot to talk about. I think first and foremost, I am a weather geek at heart. I am a first-generation college student. I had no idea what to expect going into higher education. I really had to, figure it out for myself in many ways. But I am now, as mentioned, an associate professor at Northern Illinois University, which is on the west side of Chicago in DeKalb, Illinois. In terms of AMS, I wear some different hats. I am an editor for the Journal of Applied Meteorology Climatology. I do have a CCM, the Certified Consulting Meteorologist designation from AMS, which is very interesting. I'd be happy to chat more with anyone interested here on the call of sort of what that entails. And I'm also a committee member on the Weather Analysis and Forecasting Stack Committee. So we're planning right now, hopefully, to be primarily in person for the annual meeting for WAF NWP, but of course, that will be TBD depending on how bad the Delta variant gets, and certainly encourage a lot of people to register for that particular conference, whether in person or virtually. A lot of what I'm going to talk about today is in that weather analysis and forecasting wheelhouse, but does have broader applications across atmospheric science. So I thought I would start with, as many of us, how did you get interested in atmospheric science? I was actually on a path for engineering in high school, and a little town of Granville, Illinois, Putnam County High School in central Illinois. There you can see the inset, primarily a rural sort of agricultural farming community. This tornado path intersected my high school, and naturally started asking a lot of questions. Why, what, when, is this, and then sort of seeing severe storm damage firsthand, I think really, not only seeing the physical scar right on the landscape, but also seeing the mental scar that tornadoes and severe storms influenced and impacted people. I think that really sealed the deal for me. And then I set on a path for meteorology. So probably a sort of similar story for many. Of course, there's sometimes a significant event for people that sort of sparks their interest into atmospheric science. For me, I was always interested in math and science well before then. And so this was a really nice way to apply. I think I switched majors from engineering to atmospheric science the very next day. At NIU, I'm a part of the Weather Climate Society research group. Right now we have 4 active faculty really researching the intersection of weather and climate extremes with society. So obviously climate change plays a role here, but we're also interested in things like predictability, as I'm going to talk about today, especially on the subseasonal horizon, how to go beyond what we can do with numerical weather prediction models and start to look at things like subseasonal and seasonal forecasts. So that's what I want to kind of get into today as well. But you can see we do have a cohort right now of graduate students and postgraduate students that are helping us examine some of these important questions. I think in my career, so far, the thing that has really driven a lot of the research has been losses. Here are the CPI adjusted losses strictly for severe convective storms since 1980. You can obviously see this market increase starting on or around 2006, where we really don't have years anymore where severe storms don't cause at least $10 billion in insured losses. And these are very problematic for the insurance and reinsurance sector because we're not talking about singular big events. These are usually like death by 1,000 paper cuts. You think of the Norman, Oklahoma hailstorm this year, San Antonio hailstorm event of this year. Of course, it seems Dallas, Fort Worth, and Denver are always perennial targets for these types of hail events. This is primarily driven by hail, by the way. But then the most costliest thunderstorm in United States history last year around this time on August 10th, the Midwest derecho. These types of events are, for the insurance industry in particular, are very problematic. But of course, as a scientist, we want to really understand what drives these, the variability in these events, and whether or not we would expect to see potentially more of these in the future with a changing climate. And so really that has been the nucleus for a lot of my research. And anytime one of these events happens, you can bet that I'm getting phone calls and emails from members of the media asking, was this derecho, was this extreme event due to climate change? And of course, the answer that I always give is always the same. Usually these are ill-posed questions because we're trying to directly blame climate change for a particular event. For example, the Pacific Northwest heat wave this year that I think triggered a big discussion, not only in the scientific community, but with just general lay readers of whether or not that event was directly due to climate change, or what types of events should we expect in the future. Is this sort of a blueprint, right, of a new climate? And so a lot of these stories are, they're designed for clicks, right? They're sensationalism, but they do, I think, shine light on these research problems that we are struggling with in the science of whether or not these extreme events, right, in terms of the distributions here and the edges of the distribution, are these going to become more or less likely in a future climate? That's really hard when you start talking about individual events, because the attribution science is just not quite there yet for many of the very small scale perils that we're going to talk about today, like tornadoes and hail. As you get, right, as you sort of relax the time and space constraints, heat waves, right, large scale precipitation changes, sea level rise, the link to climate change becomes a lot clearer, especially with individual events. But as we go down in scale to things like hurricanes and tornadoes, it becomes much more difficult. So the attribution science, especially when it comes to things like tornadoes and hail, again, extreme events, it becomes it becomes pretty difficult to do. So hopefully I don't have to, I think, convince anybody on this call that climate change is occurring. It is a major issue, and we know that we are the primary cause of the forcing mechanism for the recent changes that we've seen, not only in global average temperature, but things like sea level rise, Arctic sea ice loss, et cetera. And so as we move forward with any perspective we have on atmospheric climate or climatology, it's good to understand history, right, and kind of what's happening right now, but have these future projections of what is possible. Of course, a lot of this relies on climate modeling that I'm going to show here in just a minute with extreme events. That is a difficult area of research as well. But we do really want to try to understand, if forcing X is applied to the climate system, what is the response in extreme event Y? And that involves a lot of moving parts. But it is something that, as we start to build resilient communities and communities that are going to try to mitigate these types of events from happening, or at least the losses from them happening, we do want to understand the scientific component. Of course, there's a big societal component that I'm going to talk about later, but the scientific component is very important. And so I think boiling down, a very simple way to understand this research question is, are the changes we are seeing globally in things like carbon dioxide levels and forcing mechanisms associated with the greenhouse effect, are they having any impact at the very local peril scale on severe convective storms, whether that's hail, tornadoes, damaging winds, wildfire, hurricanes? You can apply this type of research question across all of the extreme weather events that we see, not only in the United States, but globally. One of the other things I want to touch on today, so that's kind of point number one, I want to address that climate change component with severe storms. I also want to talk a little bit about the understanding the variability in things like a tornado season or a hurricane season. And so here's an example of April 2011, which is probably the most active tornado month we have in recent history. You can see the inset here are all of the tornado reports as logged by the Storm Prediction Center, what we call the local storm reports. And then in the bottom right is sort of this environmental covariate. We have something called the significant tornado parameter, and we're accumulating the hours over the entire month. And so you can just kind of see subjectively here, this really strong correlation between the environment, right, that produces severe weather, in this case, tornadoes, and where they're actually reported. So some years look like this, right? Extremely active. This actually led to things like Vortex Southeast and appropriations in Congress to getting movement in studying these events in more detail. And then the first year of the field campaign in the Southeast, this is what happened, right? This was April 2016. Same exact idea, looking at the entire month here, significant tornado parameter hours in the color fill, and then the actual storm reports. So the question, right, to me is, what creates an April 2011 versus an April 2016, right? What are the drivers in the weather and climate system that either set up to, create a really remarkable tornado season from a scientific perspective, and of course impact on society, versus an April 2016, which climatologically speaking was really a record low. Okay, so that's really in this idea of climate variability. So the two things, again, we're going to talk a little bit about this climate change, which requires sort of a past, present, future approach. And then I will talk a little bit about this climate variability angle, which is understanding the forcing mechanisms that set up to create periods of enhanced extreme weather, or perhaps mitigate extreme weather. And I'm going to look at this again in the context of severe convective storms, so hail, tornadoes, and damaging winds. And then can we anticipate this, right? Can we see these periods of April 2011, for example, coming down the pike and anticipate them as society to be resilient in many ways? So a lot of my research uses emerging techniques like machine learning. That's very important for extracting signal out of noise, but also a lot of high resolution modeling using things like WRF and MPAS and the new FV3 model that has now come online, being used by NOAA's National Weather Service. I also use a lot of reanalysis data, so looking back into history and trying to extract signal out of those historical data sets as well. So this is really a big data problem. I mean, petabyte scale data problem, where you're trying to harness these large data sets that we have to be able to say something either about history, about what's happening now, or in the case of climate projections, what's happening. Well, let's take a quick look back at
the most devastating series of tornadoes in many decades rips through 6 Midwestern states. In the wake of the twisters, there are nearly 250 people dead, with damages mounting to the hundreds of millions of dollars. Iowa, Wisconsin, Arkansas, Indiana, Illinois, and Michigan were all hard hit by the deadly tornadoes as they slashed across the heart of the Midwest.
This was the aftermath of Palm Sunday, 1965. Not a single storm this time, but a large tornado family called an outbreak.
So just a quick look back, right? We often do that when we're examining anything, right? It's good to learn from history, and severe storms are no different. That was some quick video from the April 1965 Palm Sunday tornado outbreak across the Midwest. And so one of the things we do as scientists is really look back at the historical record of things like hail and tornadoes and try to understand how have they changed through history. And one of the things that you see when you do that is for strong tornadoes, EF1, say, and greater, there really hasn't been any significant trend in the number, the frequency of these events over the recorded period that we have, which really starts at about 1954 or so. And you can see here EF2, right? That line has been steady right around or just under 200 or so EF2 tornado reports per year. So we're pretty, in terms of the recorded period of history for tornadoes, those in terms of frequency really haven't changed very much. Where we've seen this market increase is in hail and wind, especially starting right around the mid-1980s. And of course, if you start to think about that a little bit more, right, this is the modernization of the National Weather Service, the introduction of things like the WSR 88Ds in the National Weather Service, detection, right, things like Skywarn, certainly a boom of chasers, storm chasers into the Great Plains in the mid-1990s throughout the 2000s. If you really look at the last 10 years or so, it actually has leveled out quite a bit. And I think we're probably in what I would call the modern reporting era, starting on around maybe 1995, 1996. There's not a lot of increase or decrease past that point. But this creates an issue, right? If you're looking at a long-term climatology, we would certainly have to normalize for things like population, technology, which create problems in the data set, right? These are anomalies. These are basically non-stationary time series when you're looking at things like hail and wind, which become problematic when you're trying to tie historical events to what actually happens at the ground with reports. So instead, one of the things that we can do is let's set aside the reports for a minute. They are super important. They are our ground truth of what's happening. But in 1950, a tornado didn't get reported in Kansas unless it probably hit a farmstead or caused some sort of injury or fatality. Of course, in 2021, there would be 50 YouTube clips up of an EF0 that happened in the middle of a Kansas wheat field, right? So we're now the reporting, right? The over-reporting or the constant reporting issue that we see now is something that we didn't deal with in the past. What we can do, though, is go back in our reanalysis data sets and look at the ingredients that form things like severe storms. So of course, if you want to bake an apple pie, you have to have certain ingredients. If you want to make a supercell thunderstorm that creates tornadoes, you have to have SLIM, right? Shear of the wind, lift, instability, and moisture. Those are the 4 basic ingredients for organized convection. And so we could actually go back in history and let's ignore the reports and just look at the environments, right, that house severe weather inside of a reanalysis data set. And one of the seminal papers that did this was by lead author Harold Brooks out of the National Severe Storms Lab, which I think is one of the most simple analyses to date of this type of environmental analysis, but it's very elegant in discriminating when and where severe weather, specifically significant severe weather, occurs. And so climatologically speaking, we see the strongest tornadoes, the largest hailstorms, the biggest damaging wind events when the atmosphere is highly unstable, right? As shown here on the x-axis as CAPE, convective available potential energy. You can think of it as, right, this sort of nuclear explosion cloud. It's just the potential energy that's available to a convective process. When analyzed against the shear of the vertical wind, just looking at deep layer wind shear. And if you kind of think of it physically, we have this fuel for the storm on the X, and then its ability to organize on the Y. And what you see is a vast majority of the significant severe weather events that we see are in this upper right quadrant, meaning they're happening in regimes of high instability and high vertical wind shear. So, and again, this type of analysis has been refined since this paper has come out, and we really do understand the background convective environment that is most favorable for significant severe weather. And what we can do is take the number of times, right, that these ingredients come together and look back through reanalysis data sets and determine when and where globally things like tornadoes would be at least favorable to happen or most common to happen. Now, this is not reports, right? We don't have people calling in reports in the Pacific and Atlantic Ocean. This is simply a reanalysis derived environmental proxy for where the environment, at least physically, could support tornadoes. And of course, in North America, we are really ground zero for supercell thunderstorms. This is a little bit biased towards CAPE. Really though, anywhere you're downwind or downstream of a northwest to north to south oriented mountain chain, you typically find steep lapse rates and enough convective available potential energy to produce strong updrafts. But there are other hot spots. Of course, South America, Argentina is a hot spot. We just, the National Science Foundation Relampago field campaign just finished up in portions of Argentina. South Africa is actually a global tornado hotspot, portions of Eastern Australia, Bangladesh, right? You seem to have tornado videos coming out of Bangladesh all the time. this type of global perspective allows us to just, I think, get a handle on when and where the ingredients come together, or potentially could come together to support things like tornadoes. A little bit coarse resolution there over the Great Plains of the US, but what happens if we take a finer resolution reanalysis and look at this? And so this could be at least objectively a way to objectively define where supercell alley is located. I say supercell in particular. This would not be the objective definition of tornado alley, because tornadoes happen in many different environmental regimes. But specifically, if you're looking for the traditional supercell, queen of thunderstorms, if you will, with rotating updrafts, this would be your objective climatology across the United States for these types of events. And so this was actually from some of my master's work, and it really runs right through the I-35 corridor, down through central Oklahoma, Dallas, Fort Worth, and portions of south central Texas. This is essentially where the ingredients come together most favorably for significant supercell thunderstorms. And so we can then do a whole bunch of cool things if we have these environmental proxies, right? We can look at how they change through time. We could look at a specific grid point like Tulsa, right, Oklahoma, for example, and begin to look at time series there of the variability. And then perhaps most importantly, we can look back in history and say, if we have a forecast for a known outcome, we can start to look at these hindcasts of events and understand maybe how predictable the setup of these particular environments, what type of predictability is associated with this particular event. And that's something we're actually actively looking at right now. So within this corridor, you have probably seen lots of severe weather videos, images. Here is a very well-known tornado from May 20th, 2013. This was one of the more Oklahoma F5 tornadoes. If you go a little bit further north, this is probably my favorite tornado event of all time. I actually have a short video of this event for you. Storm chasers will recognize this video right away, but it's the Columbus, Nebraska tornado of June 23rd, 1998. I think I have a quick video clip. Let's see if it'll play here. Shit. This is the audio very carefully.
Susan, get my pants.
So this farmsteader in Nebraska is staring down a significant tornado, and it's not moving left, right? It's not moving right in the frame. It's getting larger, so it's coming right at him. And he calls to his wife. He says, "Susan, get my pants." So this guy is staring down a significant tornado coming at him with no pants on. Probably one of the most classic lines in a tornado video ever recorded. We have other events outside of this traditional supercell alley. This was from that video I showed earlier, the historical video of the Palm Sunday 65 event. Probably one of the first pictures of really two tornadoes rotating around in the same mesocyclone. This is from Northwest Indiana, from the NOAA photo library. So we know, I think the reason I paint this picture is, we try to understand the distribution of what has happened in climate. We know that these extreme events are possible. We probably haven't seen everything the atmosphere has to offer in terms of severe convective storms, but we do have these upper end events that we know have happened and will happen again in the future. And so it at least establishes some climatological baseline for us. And so what we wanted to do is take this high resolution reanalysis that I showed on the previous slide, and Harold Brooks and I really tried to create a spatial climatology and understand really how these things have changed. How has, for example, the significant tornado parameter, which is an environmental constraint on tornadoes, how has that changed through time? And so this is a time series of the annual tornado count in blue, and then the annual accumulated significant tornado parameter across the United States. And you can see right away, just visually, there's a pretty strong correlation. No surprise that when we have high-end years of STP, we typically end up with an above average tornado count. And both of these metrics are increasing. They are statistically significant. But really since 1995, we've seen a lot of variability, right? Ping-ponging back and forth from high years to low years. This year is a very low year for severe weather activity. We've already been through peak season, May and June. The hail reports across the United States right now are probably going to be the lowest ever in recorded history. which is saying something in terms of climate variability. So we see these ups and downs. We want to better try to understand what's going on with these ups and downs. But what about, instead of looking at the US as a whole in the frequency, what if we looked at what was happening at the grid point level? And we did that. And this garnered a lot of news, right? Oh my, Tornado Alley is shifting. If you are now in Tennessee and Alabama and Mississippi, you are in the new Tornado Alley. That's not what our study showed. Our study showed that if you looked at a place like Dallas-Fort Worth 40 years ago compared to now, the threat there in terms of the significant tornado parameter and the number of tornadoes has gone down over the last 40 years. But this area of the Great Plains still remains the highest frequency for these events compared to anywhere else. So it's not that if you're in Dallas or if you're in Oklahoma City or if you're in Denver that the threat is shifting away from you. That is not happening. There is a trend over the last 40 years that is consistent actually with what our climate models are showing by the end of the century. It's just that this trend is already happening. And so the question really that we pose in this paper, what is causing this? Is this already a signal of climate change? Because as I'll show you here in a little bit, our climate models, when you look at the environment and then simulated storms in the future, it does show this sort of northeastward change in the greatest, not in the greatest frequency, but certainly increasing threats as you move towards the Mississippi River in portions of the Midwest, Southeast, and even to some extent in the northeastern United States. So this caused a lot of commotion, for better or worse. I always try to take the opportunity to get up in front of people, whether that's CNN or the Weather Channel or whatever, when they're knocking on your door asking you about this. It's usually a net positive for a scientist to get out there and be able to disseminate information about your work. And so I would encourage all of you, whether you're an early career scientist, mid-career, or late career, take that opportunity to get out there. It allows you to sort of set the story straight, be the expert that can comment on your own research, rather than letting the Facebook and whatever commentary go wild. You have the ability to go out there and be the authority on that particular subject. This was probably one of the coolest things to happen to me in my career. This was from Jeffrey Katurba. He's a cartoonist for the Omaha World Herald. And he sketched up this cartoon, which I have hanging in my office now, that says, the headline of the paper says, tornadoes shift to the east, and there's this family of tornadoes that say, I don't care, I'm not going anywhere. The head of the household has said, we are staying put, we are not moving. So sort of a tongue-in-cheek cartoon related to our research that I thought I would share with you. But I want to sum up a little bit about what history has told us about severe convective storms. Again, this sort of, when a lot of us think of extreme weather, we think of the hail pounding on the roof or the flash flooding or the wildfires. But for severe convective storms, forgot I put this in here. People in Nebraska apparently filmed tornadoes without wearing pants. Scientifically, there have not been significant changes in the frequency of hail or tornadoes across the United States. And so the people that have pushed that sort of idea or narrative are just not looking at the right data. There has not been a significant change in the annual frequency of hail and tornadoes across the United States. What there has been is an increase in the variability, sort of looking at the standard deviation from year to year. We see more years now that are high end, think 2011, but also very low end. That could also be a sign of climate change, with getting stuck in what we call blocking weather patterns or weather regimes that are either very favorable during the most prolific time of the year for tornadoes, again, early spring, mid-spring, or patterns that are just not very conducive to severe weather. Our group is really interested in understanding those modes of interannual variability. We also know that there have been spatial changes, and these spatial changes are really important for socioeconomic impacts. More people live, right? Population density increases as you go east of the Mississippi River. We know there's significant vulnerability in the southeastern United States due to trees, propensity for storms to happen at night. Mobile and weak frame housing stock is a big challenge in the southeastern United States. There are lots of socioeconomic and physical reasons that this particular increase in frequency, specifically in the Mid-South and Midwest, is cause for concern for people who are looking at dollars and cents, but perhaps most importantly, lives of when and where these threats are setting up. So that's a little bit about the history. Right now, what are we doing for tornado forecasts, alerting the public? Many of you are probably aware of things like severe thunderstorm and tornado watches. I do want to give a brief shout out, not only to the Storm Prediction Center, but also to all the National Weather Service, WFOs, the weather forecast offices, for their incredible work, especially over the last few decades, of getting where we are today, of being able to alert the public for severe weather events. We, again, understand the background environment now. We have increased our resolution of our models, which is very important for extreme events, to getting down to the resolution where we can actually resolve these extreme events in real time. There are new efforts that are emerging at the National Severe Storms Lab, like Warn on Forecasts, where one day we hope to actually be able to issue things like tornado warnings or watches based on a forecast, not based on what's happening right now. We're still a ways away from that, but it's these types of I think, big ideas that have got us to where we are now. And they translate into a reduction in fatalities and a reduction in casualties. This is from Harold Brooks at the National Severe Storms Lab, just showing the number of people that have died strictly due to tornadoes per million people since 1875. And you can see things like the advent, going from the Weather Bureau to the National Weather Service to the modernization to Doppler radar. This number keeps driving down. Many of us would argue there's going to be some sort of asymptote that we're going to hit, because we need to address the major issue nowadays of I think my number one issue of reducing things like tornado fatalities is tornadoes in mobile homes, tornadoes that impact mobile homes or weak frame housing stock. The long notion of going to your safe space when a tornado warning is issued is simply just not going to save a life when it comes to a mobile home. And so taking action perhaps at the tornado watch stage, right, when conditions are favorable. And a lot of times, for whatever reason, people don't have the means to take shelter, or they don't know what it means to take shelter, or they're not even getting the message, right? We do all of this amazing work forecasting, but it never gets translated across the finish line, which is receiving the message and acting on the message. That is always going to be a challenge when you're dealing with humans. And so no matter how good our forecasts get, we're still going to struggle with things like lowering or reducing the number of fatalities from extreme weather events to zero. And that goes across the hazards. This is not just severe weather. This is hurricanes, wildfires, take your pick. Here's an example of just how good these forecasts can be. This is an example of a day 6 forecast from the National Weather Service Storm Prediction Center, just showing how the forecasts evolved and then the actual reports themselves. And so I want to take a second here of just saying, okay, I'm giving them a lot of props, but just how good are we? Okay, I'm not going to talk specifically about the National Weather Service forecast or the forecasts at the SPC. I just want to show you how good a model forecast can be. So just how good are we at forecasting hail and tornadoes? If you're not aware, the Storm Prediction Center does issue a tornado forecast every single day. In fact, it's issued multiple times per day, but it looks something like this. This was the tornado forecast outlook for April 9th, 2015. The Storm Prediction Center issues their outlooks based on probabilities within a point, within basically a point radius. And so the forecast here for this particular day in the morning was for a 10% or greater probability of a tornado happening within 25 miles of a point within that yellow circle. In addition, the hatching just indicates that there's a 10% or greater chance that those tornadoes would be EF2 or greater. So we're looking at the possibility basically in northern, northwestern, western Illinois, far eastern Iowa, and northeast Missouri, that tornadoes that happen there, there's a much greater chance than climatology to have tornadoes there, and those tornadoes could be strong. Here's the resulting reports from that day. This was the Rochelle-Fairdale tornado that happened very close to NIU's campus. And so when you look at this forecast, right, I grade a lot of assignments, I grade a lot of exams. How do you score that forecast? So you look at that and you go, wow, you know, the forecast, you know, it did encompass an EF4 tornado, the Rochelle-Fairdale tornado. It did, you know, extend southward towards a couple of weak tornadoes that were reported in the Arklatex region. But what about the big false alarm area over Indiana, the eastward extent? How can we begin to assign this a grade, right? Would you give this a B minus? Would you give it a C plus? Would you give it an A? How do we do that? Objectively, we can do this by what's called the practically perfect hindcast. In other words, we could go look at just the reports, okay? So let's just take an example here. Just the reports, what would a perfect SPC forecast look like? Knowing that at the time that we draw the polygons for these outlooks, there's going to be uncertainty as to exactly where, right? We're not good enough right now to say Dodge City, Kansas, Peoria, Illinois, Des Moines, Iowa, we're going to get hit by a severe storm today. There are inherent uncertainties in both the synoptic scale, but most importantly, the mesoscale and storm scale that prohibit us from doing that right now. So what we could do is just kind of smooth, right, the parameter space and come up with what a perfect outlook would look like. And so maybe on a day like this, where we have some tornado reports come in, we apply this Gaussian smoother and we create a quote unquote perfect SPC forecast, okay? This would be our target. This would be what we're trying to verify. So you can imagine if, this is kind of the outcome that we wish we would have issued this forecast, but that's going to be our forecast target. That's what we're always striving to get to. And so one of the questions that I asked as a researcher is, if we have that target, which is our predict-in, could we come up with a predictor from a model to forecast the predict-in? And the predictor is going to stem from the GFS, specifically the GFS ensemble, which right now has 21 members, or actually has been expanded now with the new FV3 GFS. This was with the old spectral GFS when this forecast, when this particular study was done. But we just wanted to answer kind of a simple question. How well does a model, only knowing the environment, predict severe weather on a daily basis? Okay, so I'll point you to the paper later, but the whole idea here is we're going to use the environment just like a forecaster would do to forecast whether or not we get a practically perfect event. We're going to specifically use something called the supercell composite parameter, which is a parameter that takes instability, low level turning of the wind called storm relative helicity, and also deep layer vertical wind shear. And we're going to look at that value in the presence of convective precipitation inside of the model. In other words, did the model have a favorable environment? And did the model produce a convective precipitation signal? If it did, we'll count that as a forecast towards some sort of practically perfect predict and, okay? So we do this for several years, but basically the methodology here is to take every single 0Z GFS ensemble forecast cycle, look at all of the runs, toss out the first 12 hours and the last 12 hours so that we have 15 periods that consist of a convective day, which is 12Z to 12 Zulu, okay? So we're looking at basically the convective day, and then we're going to assign a practically perfect value, right? We can basically calculate the practically perfect for each of those 12Z to 12Z periods, and we can match up the GFS ensemble supercell composite parameter forecast, things like the mean, the standard deviation from all the members, the max, the min, all those kind of cool things that we can do with ensembles. And then we're going to pair that up with the 12Z to 12Z period. We're going to look at this for tornado and hail, and we're going to do it for the entire United States. And so visually, the methodology sort of looks something like this. This would be our forecast target. Maybe we're only interested in that 5%, right? We're going to say, yeah, 2% is kind of broad brushing. We're going to focus in on the area perhaps of greatest tornado threat. That would be what we're trying to predict. And then from the GFS, we could look at something like, where is the mean on all the members showing a signal greater than a value of 2? Okay, this is just a hypothetical. And then of course you can do your simple forecast verification statistics based on gridded extractions of each of these forecasts. So we could look at the false alarm, right, which would be all the blue area, where we hit the forecast in the purple, where we missed, and then of course all the correct nulls. When you're dealing with extreme events, you will have tons of correct nulls. So it's easy to get a very high forecast accuracy, right? Models will generally have accuracies well above 90% when you're dealing with extreme weather because they're dominated by the correct nulls. This goes back to the famous Finley tornado forecast of 1884. So what you really want to do is throw out the correct nulls and look at skill statistics that ignore that particular metric and focus really on your hits, your misses, and your false alarms. So I don't want to lead you down an entire path of study. I want to really focus on the results from that work. The citation is here at the bottom if you are interested in that paper. But really I think the most important thing that came out of that study was something called the Breyer skill score, which judges your model, in this case, the GFS ensemble, to a reference forecast. And the reference forecast here is both a random forecast and also climatology. It's referenced here on the left as climatology. And what we basically showed is that if you're going to only use something like the GFS ensemble, okay, that's going to be your sole source of a prediction, then after about 9 days, you are better off going with climatology in March, April, and May. Okay, for hail, you have skill all the way out to maybe about day 11, day 12, and then it diminishes to a Breyer skill score of 0. Basically, again, meaning after you get just beyond a week into the early portion of week 2, the dynamical ensemble models that we currently have are not capable on a daily basis. This is very important, daily basis of predicting practically perfect. Okay. That does not solve the issue of how far in advance we can predict these things, but at least from a dynamical model, we have set a benchmark. This is really important because we want to know how good we are now and what we need to improve upon. So this is really our benchmark, right? So let's just call it 10 days, 11 days that we're going to get we can squeeze some skill out of the dynamical models for prediction of these very extreme events. How then, right? And I get this question all the time. People are like, well, you just told me you can't forecast beyond 10 days. How are we going to make seasonal tornado forecasts or tornado forecasts for 3 weeks into the future or 2 weeks when our major source, our major tool is dynamical models? And the answer is we don't use dynamical models. Dynamical models are an initial condition problem. We're feeding model data in, there's a snapshot at time t equals 0, and we do numerical integration out into the future. That's a weather forecast. What we're doing at the sub-seasonal scale, so looking at predictability beyond week 1 into weeks 2, 3, and 4, we're not really looking at dynamical prediction per se. There are aspects of dynamical prediction. We're really interested in forced boundary prediction, very similar to what we do in climate models, in seasonal forecasts, but also statistical analogs and statistical dynamical approaches that can leverage the needle one way or the other, okay? So what we're really trying to understand is next week or week 3, is the United States going to be in a very favorable pattern for snowstorms? Is it going to be in a really, a pattern that would really mitigate fire weather, okay? We're not really looking at individual forecasts here. So what we really want to do at the subseasonal scale is relax the space and time constraints of this daily prediction. We may be really good at predicting a trough coming into the west and its impacts, but we're not so sure about the timing, right? And so if we relax the forecast target, then in theory, we should have greater skill. And so I want to just quickly mention too, the skill right now that we understand in the subseason, like what dominates the understanding of the prediction of skill in the subseasonal realm, which is widely accepted as 2 weeks to 2 months in advance. The primary source of prediction is tropical convective forcing, which is driven by something called the Madden-Julian oscillation. And for many of you, unless you've had probably like a climate dynamics course, you're probably like, what the heck is the MJO? The MJO is really just an oscillation of convective activity in the equatorial Indian Ocean. So across the maritime continent and then eventually into the Western Pacific Ocean. It's just looking at where the convection, where this big blob or amoeba of thunderstorm activity is located in the equatorial maritime continent. And so there have been a lot of studies that have been published, not just on severe storms, but looking at things like hurricane modulation by the MJO, wildfire, precipitation, atmospheric rivers, heat, extreme precip. We do understand that there is a statistical relationship and a physical relationship between the forcing that the MJO puts on the climate system, basically this big area of latent heating that alters jet stream structures and eventually downstream weather conditions across North America. It is the predominant driver of weather and climate variability on that subseasonal timescale across North America. So a very quick, just schematic here of what the MJO looks like. We talk about the MJO in terms of phases. So it's really in phase 1 through 8. And it's really just looking at a positioning of where the greatest outgoing long wave radiation associated with convection is located. So in other words, where is the thunderstorm? Where is the big signal of thunderstorm activity located? And so the example here would be an MJO phase 2, moving into phase 3, because you can see the, as here in the schematic, the MJO has an eastward propagation. So it'll literally start as waves coming off the coast of Africa. You'll probably see a blossoming in the convection phases 1, 2, 3. It'll move across the maritime continent 4, 5, and 6, and then eventually out past the international date line as you get to phases 8, 1, 2, and the process repeats itself. Now, one way to track this, right? You could look at satellite with your eye and say, where is that convection at? One of the ways that we track this was a great paper in 2004 called the Wheeler-Hendon diagram, where we look at the principal components of things like 850 millibar easterly wind and outgoing long wave radiation. There are different ways to track the MJO, but we can track it on this what's called phase space diagram, where the MJO, as I just kind of showed here, it goes from 1 through 8. We can track that progression using this phase space diagram, and we can actually then create even forecast of the MJO using our dynamical and statistical models. So the example that I just showed here, 2 and 3, that would be located, right? That would be an Indian Ocean MJO current phase or current stage. And then, you know, if you look at these Wheeler and Hendon diagrams, which are largely available through places like the CPC or the Australian Bureau of Meteorology, you can go look at these diagrams and track the MJO on your own. But these cycles happen on the order of 60 to 90 days. They're very well documented going back to Madden and Julian in the 1970s. Typically, they will have a counterclockwise orbit, and they provide us a way to track this dominant mode of variability. And so I was sitting here looking at this diagram one day, and I think it was the college, the softball, NCAA softball World Series. And they had, if you ever watched, they have it a lot now with baseball and softball, but they have like the strike zone and the heat zone for the hitter. So like if you're a pitcher, do not pitch this hitter low and inside, right? Because this hitter that's their favorite area, or that's their most, that's where all of their hit anomalies are or whatever. And so I'm like, what if we did that for tornadoes and hail, right? What if we looked at the anomaly in phase space of where and when these tornado outbreaks or significant events are happening? And it just so happens that for severe weather events, there's a really strong signal for severe weather events across the United States to happen when we go through what's called this 8-1-2 transition, or basically a movement of the MJO through phases 8, 1, and 2, okay? This is looked at it through atmospheric angular momentum, which I don't want to get into today. It's a different metric, but it does capture what's happening with the MJO. And we can basically plot these phase space anomalies as to, if you're a forecaster and you're looking at forecasts of MJO, whether it be 2 to 3 weeks in advance or just coming up next week, are we moving in a historically favorable teleconnection pattern that would support or favor severe weather, or in the case of phases 5 and 6, mitigate severe weather across the United States? And so physically, we have been able to show through our research that these events often happen when there's a big increase in convection in the Indian Ocean. In other words, we see a flare-up of convection in the Indian Ocean associated with the MJO. This generally increases atmospheric angular momentum, and the MJO begins to propagate across the maritime continent. In the first week that happens, right, again, we're tracing this in a counterclockwise orbit. Significant tornadoes across the United States are very unlikely. In fact, they're 8 times less likely during that first convective signal to be happening across the United States. Typically speaking, this would be a big ridge in the western United States, a trough in the eastern United States. So we'd probably have offshore flow in the Great Plains in southeastern United States. So think northerly winds into the Gulf of Mexico, probably shutting down the moisture return that is so important for severe weather, especially in the early spring and mid-spring across the central and eastern United States. About a week after that, and again, I'm showing you a very textbook event here, but about a week after that, we see a change in the global weather pattern. We see what's called a big jet extension happening across the Pacific. So the jet has become so elongated through all of this additional momentum into the jet that it's about to get ready to what we call breakdown and retract. There's probably negative frictional torque and mountain torque happening to really begin to start removing atmospheric angular momentum out of the global budget. And really what that means is we're transitioning from a very zonal pattern across the Northern Hemisphere to a very low angular momentum, which is very meridional pattern, right? Something that you would probably expect when we get a lot of extreme weather. We have big ridges and big troughs that spin up strong cyclones, lots of upper level convergence and divergence that translates to surface features, right? And so we've been able to show through our research that, if you can identify that feature happening, that there is a big statistical anomaly that occurs across the United States when we're able to detect that feature happening. In fact, about a month later, in some cases it's 3 weeks, some cases it's a month or 4 weeks. F2s across the United States are almost 15 times more likely to be occurring because the atmospheric weather regime, the synoptic pattern that you're in, is generally favorable, very favorable for things like extratropical cyclones and warm sectors that promote the ingredients necessary. So I'm going to check my time here. I want to sort of speed through some of this because we're going a little bit. I wanted to be about 10 slides ahead of this right now, but I just want to show you a case study for May of 2019, because this was a really well forecasted event from a subseasonal perspective. You can see all of the tornado warnings issued by the National Weather Service in this 2-week period in late May of 19. And I say very well forecasted. You can read more about it here at our one of our papers that we published. But watch how this evolves from MJO phase space. So we're going to look at this green, because this green is really positioning where the MJO event was 4 weeks prior to, we'll call it prior to mayhem. Okay. So 4 weeks prior to mayhem, we saw a big development of a convective signal in the Indian Ocean, the equatorial Indian Ocean. And the MJO started to get active, right? There's the phases 2 and 3, and you can see how the MJO evolved during that week. 3 weeks later, the big convective signal had moved across the maritime continent, and the MJO has progressed. These gray circles you see here are the number of United States tornado reports for each of the days that we have MJO reported, which is daily. 2 weeks prior to mayhem, here comes the MJO swinging around through phases 6 and 7. Still not a lot of activity coming through. Remember, this is early May in the US, right? Typically pretty favorable, climatologically speaking, for tornadoes. 1 week prior to mayhem, the MJO had made it all the way out to the international date line. And then week 1 and 2 of the events, you'll watch this 812 transition now that's coming. This is what we think will give us some opportunity, if you will. We're never going to be able to do this all the time, but when we have sources of enhanced predictability, or what we call forecasts of opportunity, we do think that, look at what happens here as we go from 812. This is the final transition as you go from 812. Start to see those increasing size of the diameter of the circles. That's indicating more United States tornado activity. And that period of late May 2019 was very prolific, caused lots of widespread flooding across the Missouri River Valley and portions of the Midwest, and also a significant amount of severe weather activity across the Great Plains and portions of the Midwest. And look at how this evolved from a synoptic perspective. This is 3 weeks prior to mayhem, 2 weeks. Look at how all of that MJO convection enhanced and extended the jet across the Pacific Ocean. 1 week prior to mayhem, and then you have this retraction sequence, which for really 2 weeks created a stationary long wave trough in the Western United States with southwesterly flow over the Great Plains, and classic, right, severe weather setup where you get nice poleward flux of moisture really overlapping or underlapping the moisture underneath the very adequate vertical wind shear. And so we're starting to dissect the flavor of these MJOs because they're not all the same, right? And so we're using things like machine learning to cluster them, understanding their different propagation speeds and how they alter the various practically perfect spaces. So we have a couple studies that are just about ready to be submitted. One's actually in review. And so more to come in terms of the different flavors of these events. But we really, I think as forecasters, we want to be able to hang our hat, understand when, right? I think what I'm trying to say is understand when we're going into a possible potential forecast of opportunity, or when we're going into a period of of very low skill and very low predictability for whatever reason. Maybe it's the dynamical models skill dropout. Maybe it's we're moving into a period where the MJO is going to help us, with enhanced predictability. But it's those sort of things that are happening on the subseasonal scale that cause this forced boundary response that we're going to be able to harness for some degree of enhancement of skill. So we're trying this with tornadoes. There are people trying this with precipitation. There are people trying this, of course, the CPC issues subseasonal and seasonal forecasts for temperature and precipitation, but we really want to push what's possible with other types of extreme weather. We wrote a paper on this in BAMS. Check it out. It's called the Extended Range Tornado Activity Forecast Project. Up until really last year, we had a lot of difficulty getting this funded. NOAA said this was a climate issue, and NSF said, no, this is not a climate issue. This is a forecasting issue. So it's NOAA's. So it was kind of a hot potato, subseasonal hot potato. And I think since then, there's become, I think, growing interest in this subseasonal forecasting realm that is going to help us push forward in terms of predictability. So I will say our forecasts are getting better. There are going to be these subseasonal forecasts of opportunity. They're not always there. In terms of severe weather forecasting, are we ever going to get better than that day 8 to 10? I'm not sure. We have really good models. I would argue right now we've probably hit a critical point. We've gotten to convective permitting resolution, which is right around 4-kilometer horizontal grid spacing. All right. If you've heard the term CAM, convection allowing model, the high resolution rapid refresh, the NAM nest, does it matter if we go to 1 kilometer, right? Are we going to see a lot of noise? I'm really of the camp right now that I'm not sure we're going to get much better unless we get better observation, right? And so that's this critical point, I think, is something that especially Warn on Forecast will have to deal with. Exposure and vulnerability are key. They don't often get talked about, but as I'll show here, wrapping up this presentation, we're going to continue to have these events, and the exposure and the vulnerability of the events, I think, are what's most important. So past and present, what do I see coming up in the future? Not just in predictability, but also in the potential for climate variability and change. I'm going to run through this pretty quickly. Please feel free to ask questions if we get to the end here and we have some time. I'm happy to stay on the call, but the issue is we can look at climate model projections of environments over here on the left, or we can try to explicitly resolve those perils into the future. The environments are way easy because that's what global climate models can output. They can output very coarse resolution, think tornado watch environments. If you want to get to the peril level, right, a supercell, extreme rainfall, you have to do what's called dynamical downscaling. You have to basically take the global climate model output and feed it into your own model and re-simulate the dynamics at the grid spacing that you're interested in. The environment approach has shown us, at least there's been a pretty strong consensus that in the future, we are going to have more severe weather days because of higher CAPE. So more instability, right? Higher temperatures, more surface theta E. That's going to basically win out against decreasing vertical wind shear. So you think of the thermal wind gradient. If we heat the poles, we should relax the thermal temperature gradient latitudinally, and we should see weaker vertical wind shear. But the literature is pretty apparent that future severe weather environments should become more frequent because of the increasing environments. So I'm going to kind of power through that because what I want to show you is actually some of the newer results from dynamical downscaling. So that's not looking at the environments, but instead let's look at the individual perils themselves. And this is where the modeling comes in and the significant computational expense comes in, because we're talking about running these simulations over decades, right? Instead of just making a numerical weather forecast for 48 hours, we want to look at a climate model simulation of 15 years. And of course, to do this is very computationally expensive, but what we can do is generate synthetic perils. So what you see over here on the left are basically synthetic severe weather reports. On the right, we have instability. Blue is very stable air. Red would be unstable air. We can replicate, right, what the convection allowing models do in climate models to help us understand the potential impacts of turning up CO2 into the future. And I'll just summarize a lot of that research by saying, if you look into the future, peer into the future of climate models when it comes to severe convective storms, what we generally see is not only an increase in the mean across the United States, but I think most importantly and most interestingly to me is an increase in the standard deviation. Some of the greatest high-end years in the future are in the future, but also some of the lowest years in the future are shown in this future epoch as well. There's also an increase of where we already are vulnerable to these events, and that begs the question of whether or not we're already seeing climate change unfold in front of our eyes right now this decade in terms of the way global weather patterns, at least with respect to synoptic meteorology, are responding to changes in global average temperature. So I will just say, I will preface all that and now say that more to come. We have some National Science Foundation awards that are looking at future simulations at convective scales to better understand all types of perils, whether that be severe convective storms, wildfires, mesoscale. I'm really interested in mesoscale convective systems because they provide a significant amount of the beneficial rainfall in the Corn Belt and also recharge things like the Ogallala Aquifer in the Great Plains. So stay tuned to some of those simulations, but here's just some eye candy of what these look like. We can basically, again, take global climate model output. I'm showing you 15-minute output resolution here from these downscaled simulations. So we have a lot of really cool data. Now we need to go sort through it all. And that's where I think a lot of the challenge with this type of work is done. And I will end today, because I'm over time, by talking just very briefly about the elephant in the room going forward, or what I would consider the slam dunk forecast for the future of extreme weather. And it has nothing to do with increasing or decreasing frequency of extreme events, and has everything to do with changes of the land surface. We know we're going to continue to get events like this, right? The May 20th Moore, Oklahoma tornado. This is not only going to continue to happen, but it's going to continue to happen with greater frequency. And I can say that I can sit here and tell you that with great certainty, because regardless of what happens with future severe weather events, the land use changes that we're going to continue to see throughout this century are going to alter the urban, the peri-urban, and the rural environment such that as our cities continue to grow larger, the bullseye on the dartboard continues to grow larger. And so my colleagues, Walker Ashley at NIU and Stephen Strader at Villanova, have really led the charge. I mean, it's a very simple concept, understanding that if you close your eyes and throw darts at a dartboard, right, and the darts are tornadoes, hypothetically, that as you grow that bullseye on the dartboard, you're going to have more significant, more impactful disasters when it comes to the number of housing units impacted, the overall homes, not even talking about the intensity of the swath, just talking about the number of people in the path, okay, of these types of events. And so a really cool, if you have some time this evening, go explore Google Earth Engine time lapse. You can basically go anywhere across the world and look at Google's images that they have and go back to times 1970, 1980, and look at just the changes in land use across the United States. And so here's just one example of many across Southwest Omaha from 1984 to 2016, right? The expansion of the built environment at the surface. And of course, just take a hypothetical tornado that would have happened in Southwest Omaha in the 1990s that went through completely different land use. That type of event would be way different today, given now all of the residential and commercial structures that have been built there. We have done this type of research. We know that the most important factor is not necessarily climate change. We could actually even double the number of F1 and F2 tornadoes that we see, and it would still not get to the same impact magnitude of just increasing our expected footprint by 2100 of the human-built environment. So we can do all these cool Monte Carlo simulations of the future and just taking hypothetical paths, and we can basically show that, you know, if you're an insurer or a reinsurer of severe convective storms, the annual number of housing units impacted is going to become significant by 2100, much different portfolio, right, than what it looks like now. And this is totally independent of climate change. Of course, climate change amplifies this risk even further. We cannot forget about this changing human-built environment when we talked about these types of hazards going into the future. whether that's, again, a hurricane like we're going to see potentially here in the next few days in the Northeast, whether that's wildfires burning out west, or whether that's severe convective storms across anywhere in the United States. I can say with some degree of certainty that these types of perennial $10 billion losses in the insurance sector due to extreme weather is going to continue in the future, mostly, again, just due to the increasing human footprint. But climate change still will play a role, and it's up to us as scientists, right, to try to figure out what that role is. But you can't ignore that role and not look at the change in the human-built environment. So with that, I am going to pause. I think I can see the Q&A session. So I don't know, do you want to maybe field some of the questions to me about, I tried to keep it, there's 200 people on a call. You never know what the lowest. I wanted to keep it at a level where we could sort of have some discussion. Obviously, if you want to go deeper into something, we can do that offline. But if there are any, questions that we feel like could be knocked off here, I am all ears, and I'm happy to stay on the call as long as necessary to try to get these answered.
Fantastic. Thank you so much that was just incredible. That was fantastic talk. We really, really appreciate you going through all that and sharing your research. I do want to say, for those of you that are still on the call and aren't able to stay, please join us at amsweatherband.org. We'll have more discussion in the community, and we can get more questions answered there. So please head over there if you have a burning question and can't stay right now. But there are a few that I wanted to get answered here. There's one just very basic one. Could you explain the 10% probability forecast for a tornado with plain words?
Absolutely. There's a great primer on the Storm Prediction Center webpage, but like in my own words, basically, when you see a 10%, let's say the SPC draws their forecast for the day and you're inside the 10%, what that essentially means is there is a 10% chance of a tornado report occurring within a 25-mile point radius inside of that polygon. So basically, take your home, draw a 25-mile circle, radius circle around your home, and there would be a 1 in 10 chance that you would see a tornado report in that circle. 1 in 10 chance doesn't sound like a lot, but if I told you there was a 10% chance your house was going to get destroyed today, that's probably not odds that you would want to take, right? So those types of forecasts are calibrated through years and years of forecasting to understand, what's the background climatology of tornadoes, and how do we expect the distribution of tornadoes to occur on today's date. So for things like tornado outbreaks, you'll probably see 30, 45%, maybe even 60% chance of a tornado within 25 miles of a point. And then, like I said, we can go back and grade those forecasts using the practically perfect hindcast approach.
Great. Okay, we had another forecasting question. Is forecasting good enough to have a product tailored to folks that are living in manufactured home stock so they can take action sooner or differently from others in the same area?
Yeah, absolutely. This goes back to, I think, the paradigm right now in the National Weather Service starts at sort of this broad outlook. Then it goes to maybe the mesoscale discussion, then the watch, meaning the conditions are favorable, and then of course the warning, meaning it's happening. And I think, a lot of the education to many up until this point has been, if you are under a tornado warning, that is when you need to take action, right? The threat has been confirmed by spotters, the threat has been detected by Doppler radar, whatever it is. For folks in mobile homes, that is not enough time. I mean, if I have a warning, I need to take shelter, and I better not be taking shelter inside of my weak frame housing stock, right? So the issue there, I think what we ought to start doing is, whether it's at the outlook stage, there's a high risk tomorrow, there's a tornado watch, the conditions are favorable. Have we thought about our daily plan as to how we might go about our day differently, or planning our day to be able to make sure we are in structures that are sound to tornadoes impact? And again, if there's two places that you don't want to be inside of a vehicle, and you don't want to be inside of a mobile home during tornadoes. We know this. And so I think it's just tailoring perhaps the message differently. There are already forecast products like tornado watches that exist that theoretically would hopefully give you a couple hours lead time to be able to make decisions. Now, that is totally ignoring the equity issues, and the socioeconomic disadvantages that certain populations are at. And then it just comes down to the question, like, does family X or does person Y have the means to actually vacate, right, their belongings and go take shelter somewhere? I mean, that's a totally separate issue that sometimes we struggle with, right, as warning communicators. So it's a multifaceted question that is going to require lots and lots of societal research in addition to the physical science research. But thank you for that question.
All right, wait, also Michael's asking if the IPCC, the IPCC AR6 concluded that a shift towards more intense tropical cyclones is very likely based on modeling and theory. Is there any similar evidence for a shift in the distribution of tornado intensity?
Great question. There's only like one paper right now that has looked at specifically the impacts of tornado intensity being driven by changes due to anthropogenic warming. It was done doing what's called the pseudo global warming approach. So basically we would take, a hypothetical future conditions, take a historical tornado, see how it responds to those future conditions. And those studies were limited in scope and the sample size. So it's hard to say for sure, robustly what the responses of tornado intensity are. I will just say on a very elementary level, some of the findings were storms would actually be delayed in terms of when they would form. So what we call the capping inhibition, or something that suppresses thunderstorm activity, was stronger in the future. But when those storms did form, the updrafts were indeed stronger. It's just that what we call convective initiation, or the formation of the storm, was just delayed a little bit. So the jury is, there are researchers looking at that problem, but I hesitate to give you a robust answer right now, right? In terms of, how confident we are in terms of tornado intensity being altered by global, anthropogenic forcing. But that's a very fair question that I get all the time. I wish I had a better answer for you, and maybe in 10, 15 years we will.
All right, another kind of more general question. Has climate change begun to affect the thermohaline circulation, global conveyor belt of ocean currents around the globe?
I am probably not the best climate dynamics expert to answer that question, so I would very much punt, although I have read the recent study that came out in Nature Climate Change about the abrupt potential shutdown of the thermohaline circulation. It was a very compelling paper in terms of global impacts. I do not study the thermohaline circulation, so I am probably very unqualified to answer that question, but I could probably, is that Michael, maybe connect with me offline. My email address is there on the slide, and I can definitely get you in touch with somebody who could probably better answer that question.
And then for extreme weather events, is there geographic variability and parameters such that the identification of environments suitable for extreme storms is dependent, for example, on topography or latitude and longitude?
Yeah, great question, Jason. Essentially, geography plays a huge role because geography determines what type of environments you can get. For example, in the central Great Plains of the United States, you're very often to get steep lapse rates originating from the Mexican high plateau, the Chihuahuan Desert. Those create very steep lapse rates and instability environments that are generally supportive of things like supercells and very large hail. But it's a geographic feature, right? You generally don't see those environments in, say, Florida, or they're very rare to happen in New York. So geography is certainly a constraining factor, but it has everything to do, at least in North America, with the positioning of how you get these ingredients to all come together, just like baking a cake, right? When do you get all the ingredients to come together? And that is certainly constrained by geography.
Okay, this is pretty specific, but Finley's asking, why would you use the global relative angular momentum instead of the popular RMM1 or RMM2 indices?
Well, RMM1 and RMM2 can be used in both angular momentum phase space or an MJO phase space. It just depends on what principal components you're looking at. If you're doing this for the MJO, it's looking at things like OLR. If you're looking at the thermodynamic MJO indices, if you're looking at the kinematic ones, it might be zonal velocity, for example, or velocity potential. There's lots of different ways to measure these things, but we found that angular momentum, just integrating the vertical and horizontal U wind with respect to pressure, is one of the ways we can capture how the MJO is influencing the atmosphere, right? So we have all of this blow up, let's say blow up of thunderstorm activity. How do you capture the end result of that on the atmosphere? And one of the ways, again, through research that we've discovered to do that, one really simple way is just to use atmospheric angular momentum, which is for a whole nother presentation in and of itself. And there are actually YouTube videos out there that I've talked a little bit about atmospheric angular momentum that, you know, certainly we could get, we could talk, we could talk hours about that.
Well, in light of the fact that you just made that alphabet soup actually understandable, our next question from Richard: you are an excellent communicator. Could you comment on the importance of leveraging social science and effectively communicating this type of technical information to a wider audience?
Extremely undervalued. You know, I think, first of all, it becomes at an institution like NIU, we are not just required to do research, we're required to teach. And for any of you out there who have been thrown into the classroom to teach a 100-level meteorology course, you will understand the types of barriers that scientists face when communicating to a general audience. And I've always tried to think about specific problems in the atmospheric science and explain them as if I'm trying to explain it to my family or my grandmother who never had a lick of college. And so if you're able to distill the most important aspects of the information and understand, right, and I think the hard part is not to sacrifice the scientific integrity. If you can still get your point across and then say, look, there's further reading, there's a lot more to this that we need to describe mathematically, physically, in the science aspect, but just get across the major points and communicate those major points with authority, and then have the scientific street cred to back it up at the end of the day. You know, there are, for example, media training workshops. There's communication workshops that the National Science Foundation puts on, expert witness testimony. I've tried to jump on those opportunities as they have come my way, because I think one of the things that we don't do a great job as scientists, we don't step outside of our lab enough and we don't communicate our findings enough to a broader audience. And if you don't do that, I can promise you, you can have the greatest scientific paper in the world and it'll get published in BAMS or it'll get published in Nature Climate Change or whatever, but it's going to go on a digital shelf somewhere, and a very, very small percentage of people are actually going to pick it up and read it, right? Where the value becomes they're communicating those results and what they mean to the broader public, whether it's for policy or whether it's just for curiosity. In a lot of cases, people don't really care. They're curious, right, about what we're doing, what's the latest and greatest, you know, in terms of the scientific cutting edge when it comes to things like hurricane prediction or severe weather prediction. So some of the times it's just, it's coming to their level, right? And then pulling them up with you. I'm a huge advocate for making it somewhere, right? And then turning it around and reaching out your hand and pulling up that person to your level. And I've always tried to look at science that way. And I don't attest to do a great job at it, but I've taken a lot of what I consider to be great presenters around me, whether that be at conferences or instructors that I've had in the past or mentors, and tried to take all of their best qualities and, you know, smash them into a 1-hour presentation, I suppose. But when I'm in the classroom, you know, my students would probably think I'm crazy running around doing things. But I think it's if you have a passion for it, right, you figure out what works and what doesn't. And I've been very blessed to have a lot of opportunity to have these types of presentations, whether it's in the media or to, you know, just interested people in weather on social media. And I get a lot of feedback after all of these events, and I do take them seriously. I think constructive criticism is very good. And so I welcome, you know, any type of comments, whether good or bad, about this presentation, because it certainly helps me modify when I go do these again in the future. So very long-winded answer, I'm sorry. That usually that does not work in the media, by the way. They want 30-second sound bites.
Can only imagine. Well, I don't want to take too much of your time. We've really run over, but we still appreciate you being here. And thank you so much for sharing all of this information. To those of you who didn't get your questions answered, I apologize, but please do send them to us at amsweatherband.org. We're more than happy to work with Professor Gensini to get those answered for you. So please do get in touch with us. And thank you all for sharing your time and sharing your experiences with tornadoes and just spending another hour with the AMS Weather Band. So
Wonderful.
a huge thank you to all of you and to you, Professor Gensini.
Wonderful. Thanks again for everyone tuning in. We'll see you all. Bye-bye.
Bye. Have a great rest of your day.